So like we were saying, this object can either move because it slides or it can move because it tips. And so we've chosen that we're going to look at slippage first. And so maybe what I'll say here is we're going to check slipping. Now, the question is, how do we start the problem? And you know what would be a really good idea? How about we draw a free body diagram? Wouldn't that be cool? So we're going to put a load P right there. And we got a load right here of 500 pounds. And not that it matters, but I'm going to go ahead and write this in. That's 4.5 feet up from there. And this is 1.5 feet over and 1.5 feet over like that. And so that's our situation. Now, when we're talking about slipping, we look at this problem and we know there's going to be a normal force. Now, if that force were 0, the normal force would be lined up with that 500 pounds. But this force isn't 0, or else our problem wouldn't make sense. So once this becomes a number that's larger than 0, so that this thing is being pushed this way, then this force, which would be in the middle, begins to migrate. And it's some distance over, and we don't know what that distance is. And really, in working this problem, we don't even care what that distance is. But just so that we have a number there, I'm going to say the distance is x, and I'm going to say that the magnitude of that force, that normal force, I'm going to call it n. Then we say, if there was no friction on this, this thing would slip to the side, which means that it would start moving over like that. So your thing would start to displace. But we don't want that to happen, and there's a coefficient of friction here, and so there's what we're going to call a force of friction. Now, because we're talking about impending slippage, because that's what we want to know about, then this force of friction will be equal to the static coefficient of friction, which is 0.4. So it'll be 0.4 times n. Then the question is, how many unknowns do we have here? We got n, and that's also 0.4 n, so there's just one unknown, same unknown there. And then you've got p. So we look at our unknowns, and we've got p, and we've got n. And we realize quickly that that's two unknowns. So we're assuming there's no rotation, so then that means that we can get this with summation of forces in the x and y, and maybe just to be nice, we'll go ahead and put this coordinate system for our equilibrium calculations down there. And then what I think I'll do is I'll sum forces in the y direction, assuming that that's upward. So I'll have minus 500 down plus n up is equal to 0. Now this guy here doesn't have a vertical component, and so this is a fairly straightforward situation. So then I can figure out that the normal force is equal to 500 pounds. And once I know that the normal force is equal to 500 pounds, I can then say that the friction force at impending slippage is equal to 0.4 times the normal force, which we said is 500. So then that becomes 200 pounds. And then you could argue this next step is not really necessary, but we make a living doing free body diagrams and writing out these equations. So we don't slack up on that. And so we have P to the right, minus the force of friction back to the left. That'll have to be equal to 0. So then this is 200. So then here we're saying that P, maybe you could label that max if you wanted to. So that's the maximum force that you can apply without slippage is 200 pounds. But you have to remember, this is really important that you remember this. We assumed slipping, impending slippage. So that right there, this might be the answer. And at this point in the problem, we don't know if that's the answer or that's not the answer, because this calculation here does not address tipping. And that's the other mechanism that might happen. So if we were just looking at slipping, 200 pounds would be the answer, but now we have to check tipping.